Science 10, welcome to the first video from the physics unit, okay? Today's lesson we're going to talk about a little bit of language associated with physics and science, because we talk about very, very large or very, very small numbers all the time, how we write them, how we determine what's important. So we're going to talk about scientific notation, significant figures, or significant digits, okay? You might have heard of sig digs already in some of your math classes. Hopefully you have. If you have, it'll just be a refresher. After that, we're going to get into some measurement, and accuracy about that, and then we're going to get into some graphing. Okay, so you have to review the lines of best fit, the lines of and then figuring out slope and that type of stuff. Okay, so that's on this lesson. I don't know if it'll all get into this video or not, but that's certainly in this lesson. So we're going to start with scientific notation. Okay, we'll jump right into it right now. So what scientific notation is, it's the method that scientists use to write the numbers between 1 and 10. So every number can be described in a number between 1 and 10. Okay, so and really not 1 and 10, between there, so up to 9.9. Okay, 10 itself cannot exist. There cannot be two numbers to the left of the decimal. Okay, so if you have a large number like this, 6 and 24 zeros, kilograms is the mass of the Earth. Okay, express that in scientific notation is written as 6.00 times 10 to the power of 24. Okay, and this one is written to 3 significant digits, and we usually do to 3 significant digits for our science class unless it specifies otherwise. So these are significant digits. I'll explain a little bit more about significant digits in a moment, but this is written to 3 significant digits, so 6.00 times 10 to the power of 24. And what that's saying is you are moving this decimal 24 places to the right, and it will eventually give you that number perfectly accurate. Okay, sometimes though you have to go the other one's a very, very small number, and you need to write it as a number between 1 and 10. So if you have 0.900000000045 kilograms is how much the weight of an insect is, because it's very, very light, you could express that as scientific notation right here. Okay, this one has 2 significant digits, so it's 4.5 times 10 to the power of -9, and that -9 simply says that you are moving that decimal 9 places to the left. Okay, so if you count that out, that's exactly what's going on there. Okay, notice there is always one number to the left of the decimal, and then depending on how many significant digits, you might have 1 or 2 or 3 numbers to the right of the decimal to keep accuracy. Okay, and that's important to note. Okay, so another little cheat sheet here is this in the green highlights. So if there's no sign in front of the exponent, so this is about the exponent. Okay, if there is no sign in front of the exponent like there is here, the number is going to be greater than 1. It is going to be a number that is larger than 1. If there is a minus sign in front of the exponent, you know for sure that number will be less than 1. Okay, it'll be less than 1. You know the decimal is going to be in front of that first number, so you know that to be true. Okay, there's your cheat sheet. Okay, so let's move on here. Significant digits. Okay, so significant digits, rather than going through these slides with you, I think I'm going to just list a couple examples and walk you through it. Okay, so it's important to know that any number between 1 and 9, as stated here, is always going to be considered as significant digits. Zeros is where it gets messy. Okay, if there is a 0 between significant digits, like this, it then becomes significant. So this would have 3 significant digits, as all these do. Okay, if there's a 0 to the right of a significant digit, it becomes significant. Okay, those are important little tidbits to know. Okay, especially if there's a decimal involved. Okay, so this is how we're going to work through this. Okay, so I'm just going to give you a list of examples, and you can and I'll explain my thought process here as I go. Okay, so the number 1000, okay, has just one interesting number, one non-zero number. It has 1 significant digit. Just this is significant. The reason why that is these zeros right here. Okay, what scientific notation is and significant digits does, it's all about accuracy. So you need to be very accurate in science, obviously. So the number 1,000 has one significant digit because these zeros, we don't really know what they are. They're stated as 0, but as we know in math and science from the past, this number could have been 985 rounded up to 1,000. Okay, we don't know the level of accuracy of these zeros right here. Okay, so it only has one significant digit. However, as soon as you do something like this, you write 1,000.0. This now has 5 significant digits. Okay, 1, 2, 3, 4, and then obviously your 1. So the reason why this is the case is because once that decimal 0 has been written, you know that this number is accurate at least until this point, as soon as you write that decimal in there, okay? So decimal to the right, it then has it accurate, okay? A number that's written like this, that's supposed to be a 3 and a 5, sorry. Okay, this number has 2 significant digits. These zeros are to the left, so they are not significant. Okay, if you had this number, okay, this has 3 significant digits because this 0 here becomes significant because it is to the right of your interesting or other significant digits. Okay, so that's the way. 1006, I already did an example like this, has 4 significant digits. These zeros are between the 1 and 6, so they become significant. Okay. Also, if you had just the number, it has one significant figure. As soon as you put a decimal right here, it then becomes 4 significant digits. Okay, so that's one way to look at it. Okay, so I'm going to delete this. I'm going to go to the next slide because there is a typo, and I'm going to try to fix it. So there's a typo right here down in the second point. This 200, it says it has 3 significant digits. That should have a decimal there. Okay, I'll try to fix that, but if it's not fixed and you get confused, please remember that. Okay, so here's some practice. This one has 5 significant digits. Okay, 1, 2, 3, 4, 5. Okay, this one has 1, 2, 3, 4. This one has 3 significant digits. 1, 2, 3. And this one has 4 significant digits. 1, 2, 3, 4. Okay, this 0 is not significant because it is to the left. Okay. When you're multiplying and dividing significant digits and you come up with your answers, it's important to know a few rules. So for both multiplication and division, your answer is always going to be, and is highlighted here in red. Oh, come on. It's highlighted here in red that your final answer is going to go to the least number of significant digits found in the question itself. So 4.20, okay. And 18.01, okay, it's going to go, pause that here, typo. Okay, sorry, I just paused my video for a second because I noticed a typo right here while I was doing it, so I fixed it on the fly. So like I said, it goes to the least number of significant digits found in the question. So this one is 4.20 and it has 3 significant digits. This is 18.01 grams per mole, and it has 4 significant digits. The least one is 3, okay? I had 4 significant digits in the answer. It was supposed to be written as 75.6 grams, okay? So there is 1, 2, 3 significant digits there. Another thing to remember, okay, is units. Don't forget the units. So if you have amount of moles and you have 18 grams per mole, what it's essentially asking you is how many grams of something does you have. So if there's 18.1 grams of something per mole and you have 4.2 moles of it, okay, and this will become much clearer way later in the unit. But essentially what it's asking you is how much grams of something you have. Okay, so your units are going to cancel out in multiplication and division, and whatever one's left over is your unit that you're going to be in. Okay, so this one you're looking for grams. Okay, when you're adding and subtracting, same thing, least number of significant digits. Okay, and another, okay, nope, no typo here. I thought this was going to be a typo, but it corrects it right beside it, okay? So if you have 11.2 centimeters plus 5.27 centimeters, the answer is 16.47, okay? And the correct answer is 16.5. That's how you would write it. So you can see where we're losing accuracy here using significant digits already, just in this little amount, okay? When we get into measurements, there's a cool little slide that will show you that will make this a little clearer. Okay. So always remember your units with this as well. So it's very likely that you might get a question that says, and just to keep it simple, I'll use meters and kilometers. So you might get a question that says 1,000 meters plus 1.7 kilometers equals what? Okay, and it doesn't matter which one really you convert it to. It might ask you to answer it in meters. It might ask you to answer it in kilometers. For this one, we'll just answer it in meters. Remember, you got to convert this number here if we're going to answer it in kilometers. We're going to convert this to kilometers, and 1,000 meters equals 1 km. So our answer would be 2.7 kilometers. Okay, so remember your units. Okay, always remember your units, because we're going to get into unit conversion here next, okay? So right now, you can probably go through and read the rest by yourself. You can do these practice questions and get up to page 8 done in your note packet. So you should be ready to do that now. Okay, and we'll move on to measurement soon. Alright, so I was going to stop the video there and make another one starting at measurements, but I think I'm just going to do one large video for the entire unit, other than the factor label method. You'll see it in a minute. I'll do a side video for that. Okay, so measurements and units is the next little subsection we're going to do here. And it's important to talk about because it's basically everything we need to know moving forward. So fundamental units are the building blocks of all other measurements. So if you look on page 9 of your textbook, or of your note packet, sorry, you have a little spreadsheet here. This is what it looks like. I'll actually pull mine up to show you in case you don't have yours handy. Looks like this right here. Okay, and I will note that there is an error here. Okay, this block, I don't know why it's over there. I wish it was here. Oh yes, I know exactly why it was there. Okay, because these are the fundamental things we use here in Canada, but it's not necessarily its base unit. Okay, so the base units are all under here, and they are in bold. Okay, so we have meters, we have grams, we have seconds, we have liters, we have hertz. Okay, so we have bytes. Okay, so that's important to know. Oh shoot. So this is your chart. So if you have something that is in grams and you are converting it to kilograms, you know you can just move your decimal 1, 2, 3 places to the left to get that number. Okay, so it's a good chart to reflect on all the time. They all are by 10, as you can see up here. Okay, if you have something in liter and it's telling you to switch it to milliliters, then you can move that 3. So if you have 10 liters, you can add 1, 2, 3 zeros, and you have 10,000 milliliters. Okay, so it's a good chart to use for conversions, okay? So back to our notes here, our thing. Okay, there's a standard system that we use. It's called the SI for fundamental units, okay? And it comes from the French word of Système International Units. I'm sorry if you speak French, Chloe, and my accent is awful. Feel free to correct me in our next Zoom hangout. Okay, so here our fundamental units that we use are meter, kilogram, and second. Okay, that's the main ones that we use. But like I said, for sound we use hertz, and data we use bits and stuff like that. So there are other ones, but these are the main ones that we talk about. Okay. Derived units are units made from combinations of fundamental units. So speed would be an example of one, because that might be kilometers per hour. Okay, or meters per second would be the better version. Okay, so then you might need to switch these things back and forth, and that's where the factor label method comes in later. And it's kind of a difficult task. That's why I'm going to switch it, or I'm going to make its own video for it, okay? Okay, so here's a little example if you want to do a couple practice questions. Okay, so 2.5 46.9 grams into kilograms. Like I just looked up that grams to kilogram, there are 1,000 grams in a kilogram. Grams is the base unit so that it's easy to tell. And kilo means 1,000. So I can move this 1, 2, 3 places over and I get 0.9 kilograms. Okay, and it might ask you to write it to 3 significant digits, and then it would be 0.024. Okay, it might ask you to go to 4. Just read the questions, really. It's important to do that, okay? So there's some practice questions you can try. Carry on. Okay, and here's a slide that I've been excited to show you guys because it puts it kind of all in context. Well, at least it did for me. This is where significant digits come into focus here. There absolutely is a difference between 4 centimeters and 4.0 centimeters. So if you see something written as 4 centimeters, essentially it could be anything between 3.5 and 4.4 centimeters, as shown right here. Okay, it could just be rounded and written as 4 centimeters, which often happens. However, as soon as you see 4.0, you know it's exactly at this point, it's exactly 4 centimeters. So that's where the accuracy comes in. Okay. However, if your digit is 3.6479, okay, and it asks you to write it in 3 significant digits, and you write 3.64, then you are obviously using this accuracy as well. So there's pros and cons, right? Okay. In science, we do use this though, so it's important. Okay. There's a few things when you're writing answers and you're converting things, and you're talking about, I don't know, something falling or the speed of something, and you get numbers that look like any of these, it might be something to think about. Oh, this isn't right. So the speed of a falling object, if it's 340 meters per second or 1,224 kilometers per hour, probably not going to happen because it's the speed of sound. We do have some jets that can reach that, the sound barrier now, just a few, but it's very rare that happens. So you might want to reconsider it, especially if you're talking about a pitcher throwing a ball. We're probably never going to hit these speeds. Okay, if you get any speed closer to 3.1 times 10 to the power of 8 meters per second, okay, that's the speed of light, okay? That's not going to happen, okay? And that's not the right number here. Okay, just a second here. Yes, okay, that is not a typo. That is right, and that is supposed to be 10 times 8. Times 10 to the power of 8, sorry, okay? If you get a distance, that's written at 1.5 times 10 to the power of 11. I wish these would have formatted better. Meters, that's the distance from Earth to the Sun. So somebody probably didn't run that far. And a distance of 2 times 10 to the power of negative 15. That's as small as a proton. Okay, so it's even smaller than an atom. Probably not realistic. So just some fun facts for you to have here. So I know for a fact that we've gone through graphing just last year in math, so I'm going to go through this very, very quickly. I'm going to read through my slides to you here. So it's important to write accurate graphs in science to accurately display things, and when it comes to tests and equations and things moving forward, you will get docked marks if you don't accurately write graphs, okay? So it's an important part of data analysis. Always remember that your manipulated data, or the thing that you can change, goes along the bottom, okay, or the horizontal axis, and your responding variable should go on the vertical or y-axis. I use y because this y goes down, okay? So basically, things like time would go across the bottom, okay, and distance would go across the up and down. So if we did time times distance here, so the longer that you go, the further you've traveled, okay? If you change the time easily, it would change the responding variable of distance, okay? The scale of each axis should be set so that it evenly distributes the measuring data. So if you have plots on a graph, let's say somebody was changing their time, so time and distance, you wouldn't write that they wrote 10 meters, 12 meters, 17 meters, 18 meters, just so that you could have perfect dots on it. Okay, you would go 5, 10, 15, 20, and have an even measurements along the sides. Okay, so that's very important too. Okay, The axes must be labeled, so you must have time in seconds, distance in meters, must be properly labeled, okay? The graph itself must have a title, so you might say distance over time of a car traveling from here to Medicine Hat, okay? So and then you could calculate the speed of that car, the average velocity of that car, which we will do later, okay? You must have each data point plotted. A small circle could be there, okay, and just make sure it's visible, okay? Then you're going to draw a line of best fit usually, so a line of best fit does not curve, okay? So it could curve, but for ours, we're just going to usually just draw a line that is completely straight, and it includes as many dots as possible. It doesn't always go through some, because sometimes there's 4 dots on the outside and 4 dots on the other side. So here's an example of a line of best fit. It's straight, does not touch every dot, okay? But it has the same amount on the right as it does on the left. So there's 2 here, so there's 2 dots here, and there's 3 on this side. Obviously, you can't have it perfect because there's 5. That's the line of best fit, okay? And you can use that to predict about where something's going to be at any of these times, okay? So like I said, I'm going quite quickly through this because I know we've done it already. Then we're going to talk about slope is rise over run. So how do you calculate slope? You pick 2 points. Pick 2 points on the graph. Doesn't matter which 2. It could be the very first one and the very last one. It could be 2 next to each other. Doesn't matter. Just as long as you take y2 minus y1 and x2 over x1. So remember, y is the coordinate along this axis. The y goes up and down, okay? And the x is along this axis. And you take the second one and you subtract the first one from both. And then you divide them, and that gives you the slope. And basically what slope is how many units it goes vertically for every 1 unit. And it depends on what the units are you've written on the bottom for your title. For every 1 unit, it goes to the right. Okay, and it could be a negative number because that line could be going this way, right? So remember that. The lines selected should be far apart on the line of best fit. Okay, the further apart, the better. So if you could do the very first one and the very last one way up here, it will be more accurate. But as long as you pick the same 2 for your y and your x points, then it is fine. Okay. Okay. And this is my longest video yet, but you should be good to do up to page 12 in your note packet here. Okay. So go ahead, jump into that. Some graphing practice. Lots of significant digits, lots of scientific notation practice. Make sure, I realize that this unit or this chapter isn't very long, and it seems pretty simple, I hope. But it's very, 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 very important that you know this stuff like the back of your hand here so that you can easily do them in what will be complex questions for physics, okay? So make sure that you do all this practice. That's why I've only done a few pages, and most of them are just big practice questions. Do them, okay? Take your time, make sure you know them, okay? Thanks, guys. Till next time.